A radio telescope on Earth detects a pattern that nature should not easily produce. It repeats with careful timing, carries a hidden structure, and comes from a star thousands of light years away. For a moment, it feels like humanity has finally found someone else. But the signal has spent thousands of years crossing the galaxy, and during that journey its creators may have vanished. Their cities could be dust, their planet silent, and the message still moving through space long after there was anyone left to answer. So tonight, the question is simple. Could the first alien signal we find come from a civilization that is already dead? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If we received a message from a civilization we knew no longer existed, would you still send an answer? And what would you say? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about the first alien signal we find may come from a dead civilization somewhere on Earth. Long after sunset, a radio telescope is turning beneath a clear and almost motionless sky. Its enormous dish moves too slowly to notice, following a distant star while the planet rotates below it. Inside the control room, there is no sense that history is approaching. The lights are low, the air is cool, and most of the work has already been handed to computers. They listen across millions of narrow slices of the radio spectrum, sorting through the familiar noise of satellites, aircraft, mobile networks, electrical equipment, and the restless activity of the universe itself. The night may have begun as part of an ordinary survey. A list of nearby stars has been prepared, each one observed for a short time before the telescope moves on. Some have planets. Others are simply quiet suns that happen to lie within reach of the instrument. Nothing about the target seems especially promising. It is a pale point of light among billions, too distant for any telescope to show its surface, its weather, or whatever may be moving beneath its sky. The receivers collect only a faint stream of energy, and for a while, that stream looks exactly as expected. Then, a thin line appears in the data. To the human eye, it is not impressive. There is no voice in the headphones, and no sudden alarm in the room. Radio telescopes do not usually translate the sky into the dramatic sounds heard in films. What appears instead is a narrow mark on a screen, brighter than the background around it, and confined to an unusually small range of frequencies. It lasts for several minutes, drifting slightly as the telescope follows the star. Then the observation ends, the dish turns away, and the line disappears with it. Signals like this are found more often than most people realize. Nearly all of them belong to us. A transmitter on a passing aircraft can scatter energy into a receiver. A satellite can cross the beam. A poorly shielded device in a nearby building can imitate something arriving from far beyond Earth. Even the equipment inside an observatory can create patterns that look orderly and strange. Human technology surrounds the planet with a shifting haze of radio light, and a sensitive telescope must look through that haze every time it searches the darkness. So the line is stored, labeled, and placed among other candidates. Perhaps an automated system gives it a high score because it is narrow, steady, and unlike the broad emissions made by most natural objects. Perhaps a researcher notices it hours later while reviewing the night's results. There may be curiosity, but not celebration. Anyone who has spent years listening to the radio sky has learned to distrust excitement. An interesting signal is not a discovery, it is only a question that has survived for a few minutes. The telescope returns to the same star on another night. This time, the observation is arranged more carefully. The dish watches the target, moves to an empty patch of sky nearby, then returns. If the line appears no matter where the telescope points, it is probably local interference entering through the side of the antenna. if it vanishes when the dish leaves the star and returns when the dish comes back, the possibility of a distant source becomes harder to dismiss. For a while, there is nothing. The star seems as quiet as before, and the candidate begins to resemble one more accident in a crowded spectrum. Then, close to the frequency recorded during the original observation, the line returns. It does not appear in the empty field. It follows the target, faint but distinct, and its frequency shifts by a tiny amount over time. That slow change might be caused by motion, Earth rotating, Earth moving around the Sun, or a transmitter carried around another star on a world of its own. The details are not yet clear, but the signal behaves less like something sitting beside the telescope and more like something moving through space. Messages begin to pass quietly between researchers. The original data are checked again, not only as images on a screen, but as raw measurements. Clocks are compared. Software is tested. The position of every known satellite near the beam is examined. Air traffic, deep space probes, weather instruments, navigation systems, and observatory electronics all become possible suspects. No one wants the signal to survive by being treated gently. The fastest way to understand it is to search for every reason it might be false. This caution can seem strangely calm when the possible meaning is so large. Yet science often approaches its most extraordinary moments through routine actions. Someone verifies a timestamp. Someone else checks whether a cable was replaced. An engineer asks if a local oscillator could have produced a harmonic at the same frequency. A second team, not told exactly what they are expected to find, is asked to examine the data independently. The question is broken into small pieces because the full question is almost too large to hold at once. If the line appears again, another observatory may be contacted. Its telescope could be hundreds or thousands of kilometers away, surrounded by different electronics and looking through a different part of Earth's radio environment. The source star will rise there at another hour. Coordinates and a frequency range are sent, perhaps with only enough detail to guide the observation without shaping the result. The second instrument turns toward the same ordinary point of light and begins to wait. That wait might last several nights. A signal made by technology need not be constant. A transmitter could sweep across the sky like a lighthouse, touching Earth only at intervals. It might operate during part of a distant planet's day, or vanish when that world turns its antenna away. It could be weak enough to fall below the noise whenever conditions change. Even a powerful beam might reach us unevenly after crossing clouds of charged gas between the stars. Silence would not prove that the original detection was meaningless, but every hour without a repeat would allow doubt to settle back into the room. Then the distant observatory sees it. The same narrow line emerges near the predicted frequency while the telescope is pointed at the star. Its drift is not exactly the same as before, because Earth is in a different position and the observation occurs at a different time. Yet the change fits the motion expected from a source beyond our planet. When the telescope turns away, the line fades. When it returns, the line is there again. Two instruments, separated by a great distance, have now recorded something associated with the same small region of sky. The discovery still would not be announced immediately. More eyes would be invited to look, and more ways of being wrong would be considered. A distant spacecraft made by humans might lie close to the same direction. Reflections from debris could create surprising effects. Two observatories can share forms of interference through satellites or widely used transmitters. A natural source may behave in a way that no one has recognized before. The history of astronomy is full of signals that became less mysterious as the evidence improved, and that history would sit quietly behind every conversation. Yet the atmosphere around the data would begin to change. The candidate would no longer be one curious line from one night. It would have a position, a pattern, and a record of returning only when telescopes face a particular star. Other facilities would be asked to listen, some designed for radio astronomy and others adapted for the occasion. Optical telescopes might examine the star for unusual changes in brightness. Infrared observations could search for excess heat. Old archives would be opened to see whether the same frequency had crossed our instruments years earlier without anyone noticing. At this stage, the signal would become a place as much as a sound. Each observation would point back toward the same system, perhaps one containing a known planet. That world might be a little larger than Earth, or colder, or locked, so that one side always faces its sun. It might orbit within a region where liquid water could exist, though that alone would say little about what is actually there. From so far away, it would remain unresolved, hidden in the light of its star. The signal would be the only detail sharp enough to separate from the distance. People outside the small circle of observers might notice unusual activity before any formal statement. Telescope schedules could change. Data normally released at once might be held for careful review. Researchers who rarely speak to one another could appear on the same private calls. But secrecy would be fragile, and complete secrecy would not be the goal. A claim this important could not belong to one observatory or one group. It would need open evidence, independent confirmation, and enough time for skeptical experts to look for weaknesses. When the news finally reached the public, it might sound far less certain than the headlines around it. Astronomers would describe a candidate of unknown origin. They would explain what had been ruled out and what had not. Words such as confirmed, intelligent, and message would be used with care, because each one makes a different claim. Confirming that a signal comes from beyond Earth is not the same as confirming that it was built. Showing that it was built is not the same as understanding what it contains, and understanding its contents would still tell us nothing immediate about whether its makers remain alive. During those early days, the deepest change might be almost invisible. The night sky would look exactly as it had before. The stars would not brighten, and no object would move between them. Daily life would continue under the same sun, yet one direction in the darkness would no longer feel empty. A point too faint to see without a telescope would now carry the possibility that thought had emerged somewhere else, shaped matter into instruments, and placed energy into the sky with enough order for another species to notice. But even this possibility would arrive without the comfort of a conversation. The star might lie hundreds or thousands of light years away. The energy reaching Earth tonight would have left while generations passed here, perhaps before our oldest cities existed. Whatever event produced it would not be happening now, in any sense we could share. We would be receiving a preserved moment, carried across the galaxy at the fastest speed nature allows, while the source continued through an immense span of unseen time. The observers would not yet know whether the line was a deliberate transmission. It might be leakage from a powerful system never intended for us, the distant equivalent of radar spilling beyond a horizon. It could be a navigation beacon, a scientific instrument, or an automated signal addressed to no particular world. Its repetition might hold information, or it might only keep time. Even if its structure proved artificial, the meaning behind that structure could remain unreachable, shaped by senses, mathematics, and experiences unlike anything on Earth. For the moment, however, interpretation would have to wait. The signal would continue to be measured with almost painful care. Its bandwidth, timing, polarization, strength, and drift would be compared from night to night. Researchers would ask whether known stars, plasma, magnetic fields, or other natural processes could create the same behavior. They would search for hidden patterns without assuming that every pattern was language. Each test would make the mystery smaller in one way and more serious in another. Some explanations would fall quickly. Others might take months. The signal could fade for long periods and return without warning, leaving the world uncertain whether it had heard a distant machine or merely encountered a phenomenon not yet understood. That uncertainty would not be an empty space between ignorance and knowledge. It would be the central experience of the discovery, a quiet, disciplined tension between what the data appear to suggest and what the evidence can honestly support. And somewhere beneath all the public debate would remain a simpler image, a telescope moving under the night sky, returning again and again to one unremarkable star. The machine would listen without fear or hope. It would collect whatever arrived, whether it was a message, a beacon, a natural rhythm, or the last faint trace of something that ended long ago. Finding the signal would be extraordinary, but before humanity could call it a message, every natural and human explanation would have to fail. That process would begin close to home, because Earth is the loudest source of false alien signals we know. The planet is wrapped in transmissions from communication satellites, navigation systems, military radars, weather stations, aircraft, ships, phones, and devices never designed with radio astronomy in mind. Many of these signals are predictable, but some arrive through reflections, damaged equipment, or unusual paths through the atmosphere. A transmission can enter a telescope from the side, change as an object moves, and vanish just as the dish turns away, creating a surprisingly convincing imitation of something far beyond the planet. The observatory itself would be treated as a suspect. Engineers would inspect the receivers, amplifiers, cables, clocks, and computers that handled the observation. A small electronic component can produce tones at regular intervals. Two harmless frequencies can mix inside an instrument and create a third that appears nowhere in the surrounding environment. Even a cooling fan, a faulty power supply, or a nearby digital camera can leave a narrow trace in sensitive data. If the signal appeared only when a particular machine was running, the mystery might end inside the same building where it began. Researchers would compare the candidate with recordings made before and after it appeared. They would look for weaker copies at related frequencies, signs that often reveal a human transmitter or an instrumental effect. They would examine whether the line entered several parts of the receiver at once, whether it followed the telescope's pointing precisely, and whether its strength changed in the way a true source in the sky should change. None of these tests would feel dramatic on its own, yet together they would begin to close the ordinary exits. Observations from widely separated telescopes would carry unusual weight. Local interference near one facility should not appear in the same way at another observatory across an ocean. A satellite might be visible to both, but its motion could be reconstructed. A source associated with a distant star would rise and set with that star, returning according to the slow geometry of the sky, rather than the schedules of human machines. If several independent instruments detected the same narrow signal from the same coordinates, its origin would be pushed steadily outward. Even then, distance would not make it artificial. The universe produces radio waves almost everywhere. Stars release powerful bursts. Clouds of gas glow across broad bands of frequency. The remains of dead stars can flash with astonishing regularity, and active galaxies can send enormous amounts of energy across space. Nature has surprised astronomers before, sometimes by creating signals so orderly that they briefly seemed engineered. When pulsars were discovered, their pulses arrived with such precision that the possibility of intelligence could not be ignored at once. The explanation turned out to be stranger in a different way. Rapidly rotating neutron stars, dense remnants left after massive stars collapsed, sweeping beams of radiation across Earth like cosmic lighthouses. Other objects have since produced brief radio flashes, repeating bursts, and patterns that remain difficult to explain. Regularity alone is not enough. The sky contains clocks built without hands and beacons built without builders. The candidate would therefore be compared with every natural source known to behave in a similar way. Astronomers would study the star itself. Is it active, unstable, or surrounded by charged gas? Could a planet with a strong magnetic field be interacting with its sun and creating radio emission? Is there an unseen compact object nearby? Measurements at other wavelengths could reveal flares, heat, X-rays, or changes in brightness occurring at the same time. A natural explanation would need to fit not only the radio line, but the wider environment that produced it. One feature would draw particular attention: the signal's narrowness. Natural radio sources usually spread their energy over a range of frequencies because they involve vast numbers of particles moving under different conditions. A transmitter can place energy into a much thinner channel. Human radio technology does this constantly, using narrow frequencies to carry information efficiently and to keep signals separate. A line far narrower than known astrophysical emissions would not prove technology, but it would be difficult to ignore. Its frequency might also drift. As Earth rotates and moves around the Sun, our motion changes the frequency we measure by a small amount, much as the pitch of a passing vehicle changes for someone standing beside a road. A transmitter on a rotating alien planet would add another motion, and that planet's orbit would add another still. With enough observations, researchers could attempt to separate these overlapping changes. A repeating curve in the drift might reveal a day or a year on a world that could not be seen directly. This would be one of the quieter forms of evidence, hidden not in what the signal says, but in how it moves. A terrestrial transmitter usually shares some of Earth's motion, while a source fixed against the distant sky follows a different pattern. If the measured drift matched a location near the target star and repeated over time, it would become increasingly difficult to explain as an accident near the telescope. The signal would begin to carry the motion of its source like a nearly invisible signature. Timing would offer another path. The pulses might be separated by equal intervals or arranged in groups that do not resemble any known natural rhythm. Simple sequences could appear, counts that rise, gaps that repeat, or bursts divided in ways that suggest deliberate control. Yet the researchers would have to be careful. Human minds are exceptionally good at finding patterns, including patterns that do not exist. Random noise can form brief sequences by chance, especially when enormous volumes of data are searched for anything unusual. For that reason, a convincing pattern would need to continue beyond the portion that attracted attention. If a sequence appeared to count upward, it should keep counting when more data arrived. If the timing followed a mathematical rule, that rule should predict pulses not yet observed. A pattern becomes stronger evidence when it risks being wrong. It must do more than explain the past. It must tell the telescope when or where to listen, and then survive the test. The most compelling structure might not look like language at all. It could be a repeated frame with small internal changes, suggesting that the signal carries organized information. Some sections might remain constant, serving as a marker, while others vary in a controlled way. The transmission could have levels, intervals, or polarization states that are unlikely to arise from a single natural process. Researchers would search for compression, error correction, and repeated boundaries, not because aliens must use our methods, but because any message crossing interstellar space may need ways to remain recognizable after noise has damaged it. Still, there would be a danger in expecting the unknown to resemble us. A civilization shaped by another planet might communicate through principles we have never used. Its signal could be produced for machines rather than biological listeners, or it might serve a purpose unrelated to communication. What appears meaningless could be densely encoded. What appears simple could be a calibration tone. Even a genuine technology might reveal no obvious message. Just as a distant observer receiving one fragment of Earth's radar would not hear a greeting or learn our history. Months could pass while this work continued. Public interest might rise and fall, Yet observatories would keep returning to the star whenever it was visible. More data would either weaken the candidate or make it more difficult to dismiss. Natural events often change with the conditions around them, while designed systems can maintain precise behavior across long periods. But machines can fail, and nature can be remarkably stable. No single quality would create certainty. The case would have to emerge from many independent details, agreeing with one another. Perhaps the signal would occupy a frequency where the space between stars is relatively quiet. That choice could be coincidence, or it could suggest that the transmitter was designed to be noticed. Perhaps the pulses would contain a sequence based on prime numbers, quantities that do not depend on any spoken language or local unit of measurement. Such a sequence would be hard to produce through ordinary stellar activity. Yet, even then, scientists would hesitate, testing whether their own processing software had imposed the pattern or selected it from noise. Fresh teams would receive untouched copies of the raw observations. They would use different software, different assumptions, and perhaps different methods of removing interference. If all of them recovered the same timing and frequency structure, confidence would grow. The result would be strongest if the signal could be predicted and observed again by telescopes that had no connection to the original analysis. Repetition would turn an extraordinary claim into something the world could inspect. At some point, however, the remaining natural explanations could become less believable than the artificial one. The line might be far narrower than any known cosmic source. Follow the motion of a planet, appear only from one distant system, and carry a sequence that predicts its own future pulses. Several telescopes might record it independently, while every search for satellites, equipment faults, and human transmitters returns empty. None of these clues would stand alone, but together they could form a shape that nature has never been seen to make. Such certainty would be both clear and strangely incomplete. Humanity might know that an instrument existed without knowing its design. We might recognize intention without understanding the intended meaning. The signal could contain a library, a warning, a map, or nothing more than the repeating identity of a machine. It might have been sent toward Earth, toward another destination beyond us, or simply allowed to spread into space as a side effect of some distant activity. Attempts to decode it would begin immediately, but there is no guarantee that intelligence creates easy translation. Mathematics might provide common reference points, yet even mathematical ideas must be represented through choices about timing and structure. Images require agreement about dimensions and order. Language depends on bodies, environments, and histories that we would not share. A message could be perfectly preserved and still remain closed, its meaning present in the data, but inaccessible to every mind on Earth. The absence of meaning would not reduce the discovery. A narrow, controlled transmission from another star would already tell us that matter had awakened there, in a familiar way. Something had learned to measure, to build, and to shape energy with precision. Somewhere beyond our sky, physical processes had become decisions. The signal would be evidence, not merely of life, but of a world that had developed memory outside the living body, and tools capable of reaching into the dark. Only after the arguments over interference, nature, and pattern had begun to settle would attention turn fully toward the star itself. Its light would provide a distance, and that distance would place the signal on a timeline. The transmission entering our telescopes would not show us what exists there tonight. It would show us what existed when the waves began their journey, perhaps centuries or millennia before anyone on Earth learned how to listen. That delay would change the meaning of every pulse. A repeated beacon might no longer be evidence of something repeating now. A message could describe a world that had already transformed. Even the motion hidden in the signal would belong to an earlier sky, preserved across an emptiness so large that the present could never cross it. And once the signal had survived every test of its origin, another number would begin to matter more than any frequency: the distance it had crossed to reach us. Astronomers may already know that number with reasonable precision. The target star could have been measured for years, its tiny, apparent movement tracked against more distant stars as Earth traveled around the Sun. Other observations might reveal its brightness, temperature, and motion through the galaxy. What once seemed like a simple entry in a catalogue would now become the address of the most important signal humanity had ever received. Suppose the star lies 1,000 light-years away. The phrase sounds like a measure of distance, and it is, but it also carries a date. Light moves through empty space at nearly 300,000 kilometers every second, fast enough to circle Earth several times in the space of a heartbeat. Yet, the gap between stars is so large that even light needs years to cross it. A signal from 1,000 light-years away has been traveling for 1,000 years, no matter how advanced the machine that sent it may have been. The pulses arriving at the telescope tonight would therefore have left their world around the time medieval cities stood on Earth. While the signal crossed the darkness, entire human societies rose and disappeared. Languages changed, borders moved, and generations lived without knowing that a transmission was already on its way. Radio astronomy did not make the signal begin. It only allowed us to be present when the journey ended. Nothing we could do would reveal the source as it exists now. The star's visible light is delayed by exactly the same distance, so every image of the system would show the same ancient period. If a planet could somehow be photographed beside it, its clouds, oceans, nights, and seasons would all belong to a world 1,000 years in the past. The present would remain hidden behind a wall that is not made of matter, but of travel time. This delay is not an imperfection in our telescopes. A larger mirror could collect more light, and a more sensitive receiver could detect a weaker transmission, but neither could make information arrive before it crossed the space between us. There is no sharper instrument that can look around the delay, and no calculation that can reconstruct events whose light has not reached Earth. The distant system has a present, but that present is physically unavailable to us. For a nearby star, the separation might be only a few years. That would still prevent a normal conversation, though the silence between messages could fit inside a human lifetime. A question sent to a world 10 light-years away could not receive an answer for at least 20 years, assuming someone replied immediately. Every exchange would move at the pace of generations rather than speech, but patience could still give each side a response. At 100 light-years, the situation changes. A reply sent from Earth would arrive a century after we transmitted it, and any answer would return another century later. The scientists who wrote the message would be gone. Many of the people who decided what humanity should say might be remembered only in archives. Contact would become a project inherited by people not yet born, each generation maintaining instruments for an answer promised to the future. At 1,000 light-years, even that kind of exchange begins to lose its familiar meaning. If Earth answered tonight, the reply would reach the source around the year 3000. A response sent back at once would arrive here near the year 4000. Civilizations would not be speaking to one another across a table. They would be leaving statements in time, hoping that something capable of listening still existed at the other end. The age of the signal would also reshape the question of its creators. 1,000 years is not especially long for a planet or a star, but it can be enormous for a technological society. On Earth, the period since our earliest radio experiments is little more than a century. No one knows whether a civilization that learns to transmit across space usually remains recognizable for thousands of years, changes into something else, moves away from its home world, becomes quiet, or ends. We often picture alien contact as a meeting between two living worlds. One side speaks, the other hears, and some slow relationship begins. Distance replaces that scene with something less comfortable. The sender we imagine is not necessarily the sender that exists. The minds that designed the transmitter could belong to an age already remote on their own planet. Their descendants might no longer remember the project, even if their civilization survived. The transmission itself could be much older than the moment it left the star. It may have been created by an automated system repeating material composed centuries earlier. A beacon could preserve names, measurements, or images from a culture that had already changed before the waves began crossing space. By the time Earth receives the information, we may be looking through several layers of delay. An old message, broadcast long ago, from a world seen only as it was then. There would be no timestamp we could assume how to read. The signal might contain one, but its creators would not share our calendar or our definition of a second. Astronomers could measure when each pulse reached Earth and estimate the travel time from the distance to the star, yet the age of the content might remain uncertain. A recording could have been transmitted immediately after it was made, or stored for 10,000 years before an antenna sent it toward the sky. Even identifying the correct star might not fully solve the problem. The transmitter could be moving between stars, carried by a probe or a vessel far from its place of origin. It might orbit a cold object too faint to see, with a brighter star only appearing nearby from our viewpoint. The signal's changing frequency and direction could eventually reveal some of this motion, but tracing it backward through centuries would carry uncertainty. The address in the sky may be where the message came from, not where its makers lived. Still, distance would offer a rough historical frame. If the source were 500 light-years away, the signal began its final journey before telescopes existed on Earth. At 5,000 light-years, it departed before the earliest known cities. From the far side of the Milky Way, it could have traveled tens of thousands of years, beginning when humans lived in a world of ice, unfamiliar coastlines, and animals now long extinct. The farther the source, the more the discovery would resemble archaeology performed with light. Archaeologists on Earth uncover walls, tools, and bones left in soil. Radio astronomers would receive a structure preserved in electromagnetic waves. Nothing physical from the transmitter would need to survive at its origin. Once released, the signal could continue outward even if the antenna failed a moment later, carrying a thin imprint of technology through regions its makers might never have visited. Unlike an object buried in the ground, this relic would not wait in one place. It would expand away from the source, becoming weaker as it spread, passing countless stars without being noticed. Earth would intercept only a small part of it, perhaps for minutes, perhaps for years. After crossing the planet, those waves would continue into space. The moment of reception would be a brief meeting between our instruments and something that had been traveling long before those instruments were built. This makes the act of listening feel less passive than it appears. A signal can cross the galaxy and still vanish without consequence if no receiver is pointed toward it at the right time and frequency. Humanity may already have been passed by faint transmissions that disappeared into the background or arrived before radio telescopes existed. Others may be approaching now, destined to reach Earth after our observatories have changed or after our own period of radio technology has ended. The candidate in our data would be one survivor of that enormous uncertainty. It would have left its source in the correct direction, remained detectable across interstellar space, entered the region occupied by Earth, and reached a telescope while someone was collecting the right measurements. None of this would mean it was intended for us. It would only mean that for a short time, our planet and the transmission happened to occupy the same line through the galaxy. Knowing the distance might allow astronomers to calculate how powerful the source needed to be. A signal sent broadly in every direction would require immense energy to remain detectable after 1,000 light-years. A narrow beam could travel farther with far less power, but Earth would need to lie within it. If the beam moved, its brief appearances could mark the slow sweep of an antenna. If it remained fixed, our planet may have been selected, or we may simply sit behind whatever target the sender truly intended. That distinction would matter deeply. A signal aimed at Earth would suggest that the sender once knew something about this solar system. But because their view of us would also be delayed, they could only know Earth as it appeared when our light reached them. A civilization 1,000 light-years away, transmitting 1,000 years ago, would have aimed its message based on an image of Earth from roughly 2,000 years before the present. They could not have seen our radio towers, cities, or spacecraft. At most, they might have detected a living planet and decided it was worth calling. If the transmission were older or the distance greater, even that becomes less likely. They may have seen Earth before human civilization, perhaps before our species existed in its current form. The message could have been sent toward the Sun because an automated survey found oxygen in our atmosphere, or because the geometry of the system looked promising. We might be receiving a question addressed not to humanity, but to whatever life eventually became capable of answering. There is something quietly unsettling in that possibility. The signal could know nothing about us, while its arrival would change everything about how we see ourselves. Its creators may have acted without urgency, sending the same pattern toward thousands of worlds, and expecting no reply within their own lives. They might have understood interstellar communication as an exchange between civilizations separated not only by space, but by history. Humanity would have to learn the same patience. Any answer would be written for recipients we could not observe in the present. We would not know their language, their condition, or whether the receiving equipment still operated. The message might reach a thriving world, an altered civilization, an empty planet, or a machine continuing its duties without supervision. Sending it would be an act based on evidence from the past, and trust in a future no one involved would live to see. Meanwhile, telescopes would continue gathering the old light of the system. Changes might appear over months or years, but they would only reveal later, moments within the same distant era. If the signal stopped, we could not know whether the transmitter had just failed, whether the beam had turned away, or whether the final pulse had actually been sent centuries ago and only now reached us. Every event would arrive late, while still feeling immediate on the screen. This is one of the strange effects of astronomy. Seeing and remembering become almost the same act. The moon is seen a little more than a second ago, the sun roughly 8 minutes ago, nearby stars years ago, and distant galaxies millions or billions of years ago. The farther we look, the deeper the delay becomes. An alien signal would make that familiar fact personal. We would not merely observe an old star. We would receive evidence of choices made by unknown beings in a time we can never enter. The question of whether they were still alive could not be answered by the transmission alone. A continuing signal would only show that the source continued during the period currently reaching us. A sudden ending would reveal silence in that same old period, not the condition of the world today. There could be centuries of later transmissions still traveling behind the last pulse we had received, or there could be nothing following it across the dark. So the distance would give the discovery its age, but not its final meaning. It would tell us when the waves began traveling, not why they were sent, or what continued after them. To understand what might still be waiting at the source, we would have to ask what kind of transmission had crossed that distance in the first place. The most familiar possibility is a message sent deliberately into space. It is the version of contact carried through stories for generations. Another intelligence discovers that it is not alone, chooses a star, and speaks. Such a transmission might begin with simple patterns that separate it from nature, followed by information about the sender or its world. If Earth were the intended destination, the beam may have been aimed with extraordinary care. across hundreds or thousands of light years. Even a small error would carry it far beyond the solar system. The sender would need to predict the motion of our star during the signal's journey, directing the transmission not toward where the sun appeared in its sky, but toward where the sun would be when the waves arrived. That single act would reveal patience, accurate astronomy, and a willingness to address a future they could not observe. Yet a direct message raises an immediate difficulty. Long before human technology became visible, Earth offered little proof that anyone here could listen. A distant civilization might have detected oxygen, water, and other signs of life in our atmosphere, but those signs would not reveal radio telescopes. They could only suggest that the planet was alive. A transmission aimed at us may therefore have been sent as an experiment, one signal among many directed toward worlds where intelligence might eventually appear. The message could repeat for years, centuries, or much longer. Repetition would give unknown listeners time to find it and recover portions lost in noise. The beginning might return at regular intervals, allowing a civilization that noticed the broadcast halfway through to reconstruct its structure. What seemed like a simple pulse pattern during the early observations could be the edge of something enormous, a cycle so long that no individual researcher would hear it complete. Decoding such a message would begin without knowing where one symbol ended and another began. Researchers might convert changes in frequency, timing, strength, or polarization into possible units, testing many arrangements to see whether stable structures appeared. A sequence of numbers could provide a key. Repeated dimensions might suggest an image, but each interpretation would carry the risk of placing human expectations into unfamiliar data, turning an alien machine into a mirror of our own habits. A transmission meant to be understood would probably account for this problem. Its opening could teach the rules used by the rest, beginning with relationships simple enough to verify and slowly building toward richer ideas. Even then, understanding would not be guaranteed. A sender might assume senses we do not possess, or treat concepts as basic that emerged from conditions unique to its world. The message could be clear by its standards and remain almost opaque by ours. There is also no reason to assume that a deliberate message would be friendly, threatening, or emotional. It may resemble a scientific record more than a letter. It could describe a star, list measurements, or announce the presence of a transmitter without revealing anything personal about its builders. The vast delay would make urgency almost useless. A warning would arrive too late to guide events at its source, and a request for help would be older than every nation now able to hear it. But the signal may not be a message at all. It could be a beacon designed only to be found. A beacon does not need to carry a detailed account of its creators. It needs to remain distinct, predictable, and visible across distance. Its task may be no more complicated than repeating a mathematical pattern and indicating where further information can be found, perhaps at another frequency or during a particular time. Such a device might function like a signpost placed beside an interstellar road. It could help distant probes navigate, mark the location of a settlement, or provide a stable reference for machines moving through a planetary system. Earth may simply lie beyond its intended users, catching energy that escaped along the same line. The regularity that makes it obvious to us could exist, because local vehicles or instruments once depended on it. A navigation beacon might reveal motion through its timing. Signals from several locations could form a network, though at first we might detect only the strongest member. Astronomers would search nearby stars and neighboring frequencies for related patterns. A second source with matching structure would transform the interpretation, suggesting not one isolated transmitter, but a system spread across space. The map might slowly appear before we understood who had drawn it. The beacon could also be a monument. A civilization aware that its own period was ending might build a transmitter to preserve evidence that it had existed. Stone can survive for thousands of years on a quiet surface, But even stone is buried, eroded, or broken by geology. A machine that continually releases a simple pattern into space could carry that evidence far beyond the planet, though only while its power and components remained intact. It would not need to tell its full history. The lasting statement might be only a sequence that nature is unlikely to produce, repeated with enough energy to cross the dark. We were here. We understood numbers. We learned how to reach beyond our sky. Everything else could be absent, either because it was too difficult to encode for unknown minds, or because survival, not explanation, was the purpose. Another possibility is less intentional, and perhaps more likely. The signal may be leakage from ordinary technology, never meant to leave its home system. Earth has been doing this for more than a century. Radio and television broadcasts, powerful radar, communication links, and signals exchanged with spacecraft all release some energy into space. Most become extremely weak with distance, but a sufficiently sensitive receiver placed along the right direction might detect the strongest emissions. Leakage would not sound like a greeting. It might arrive as brief sweeps from planetary radar, repeated pulses from a tracking system, or fragments of communication whose content could not be separated from noise. A rotating planet would carry the transmitter in and out of view, causing the signal to rise and fade with a regular day. Seasons, orbital motion, and changes in technology could slowly alter the pattern. This kind of signal could reveal more than its creators intended. Its timing might expose the length of their day. Its changing frequency could trace the orbit of their planet. Several transmitters appearing at different times might suggest activity across a surface or among orbiting structures. Without decoding a single word, astronomers could begin to estimate how the technology was distributed and how long it remained active. Yet, leakage is fragile. As radio waves spread outward, their energy thins across a growing area. The transmissions that fill our cities become almost unimaginably faint between stars. Detecting a distant equivalent would require a powerful source, a large receiver, favorable geometry, or a civilization using energy on a scale beyond our own. If the candidate was strong and steady across a great distance, a narrowly directed beacon would often be easier to explain than the accidental noise of everyday life. There are stranger possibilities. The signal might come from a scientific instrument built to study the star, a high-energy experiment, or a method of transferring power across space. It could be part of a communication link between two distant machines, with Earth positioned briefly inside the beam. We would be overhearing one side of an exchange never addressed to us, unable to detect the intended receiver or the reply traveling along another path. If that link carried dense information, its structure might appear almost random. Efficient communication often removes obvious repetition, because predictable patterns take up space without adding new content. A highly compressed alien transmission could therefore resemble noise unless we recognize the boundaries and rules behind it. The simplest beacon might look more intelligent than the richest message, simply because it was designed to be noticed. This creates an uncomfortable limit. Proving that a signal is artificial may be possible even when proving what it does is not. Its narrow frequency, controlled timing, motion, and repeated structure could rule out known natural sources. But none of those qualities would tell us whether we had found a greeting, a radar beam, a navigation marker, or the background activity of a world going about its ordinary life. Human technology offers a useful comparison. A distant observer who detected airport radar would learn that Earth contains machinery, but not that the pulses help aircraft land safely. A television carrier could reveal a transmitter even if the images and voices were too weak to recover. Communication with a probe might seem like a beacon from deep space, while a military system could be misunderstood as a public announcement. The physical signal does not carry its purpose openly. Our own interpretations would change as more data arrived. A perfectly repeated sequence might initially seem like a beacon until small variations revealed hidden information. A signal that appeared only briefly could resemble leakage until it returned on a precise schedule pointing toward different stars. What looked like one transmitter might prove to be several sources overlapping. Every answer would remain temporary, waiting for a longer observation to alter the shape. The duration of the transmission could provide another clue, though not a certain one. A short burst might come from a momentary event or a passing beam. A signal lasting decades could belong to stable infrastructure. A pattern continuing for centuries might suggest automation, cultural commitment, or a system designed to outlive those who built it. But because of the delay, we would only learn the duration as the waves arrived. The broadcast could already have ended while our receivers remained inside its long traveling stream. If a recognizable beginning appeared again after several years, the cycle could be mapped. Researchers might discover that the full transmission repeats, placing an upper limit on the amount of unique information it contains. If no beginning returned, the message could be longer than the entire period of human observation. We might spend generations listening to a library that never repeats, never knowing whether its final section had been sent, or whether the source still added new material. There would be pressure to answer before these questions were settled. Some would argue that any confirmed technology deserves a reply, even if Earth was not the intended listener. Others would say that responding to an unknown system across a great distance is meaningless or unwise. Yet, the practical urgency would be small. A response would take centuries to arrive, and waiting several years to understand the source would barely change that timeline. During that wait, the tension would spread beyond the signal itself. Astronomers would use every available telescope to study the star and any planets around it. They would search for unusual heat, atmospheric chemicals, artificial illumination, large structures, or other signs of technology. Each result could support one interpretation and weaken another. A living, active world might produce several kinds of detectable activity, while a solitary beacon could remain after every other trace had faded. But all of those observations would share the same limitation as the radio waves. They would not reveal the system as it exists tonight. The planet, if there was one, would remain a distant point hidden beside its star, and every photon reaching Earth would belong to the era when the signal began its journey. We could compare the transmission with its world, but only with the world's preserved past. That past might still contain clues. A changing atmosphere could suggest industry or biological activity. Excess infrared light might reveal large-scale energy use. Repeating shadows across the star could show orbiting objects. None would provide a clear view of streets, machines, or living beings, and some could have natural causes. The source would have to be reconstructed from incomplete traces, like a landscape described by its heat, its chemistry, and one narrow voice crossing the night. Whatever the transmission had been meant to do, the only place capable of explaining it would remain hidden inside the old light of its star. That light would become the subject of an effort unlike any other in astronomy. Telescopes around Earth and in space would turn toward the source, collecting every wavelength they could reach. The star might still look like an ordinary point, but its light would contain small disturbances created by planets, dust, gas, magnetic fields, and perhaps technology. Nothing would offer a direct view of the beings we hoped to find. The system would have to be rebuilt from shadows and slight changes in color. The star itself would provide the starting point. Its temperature, age, mass, and activity could be estimated from its spectrum and brightness. A quiet, stable sun would create one kind of environment, while a young star throwing frequent flares would create another. If the star were nearing the end of its life, the signal might come from a society already facing a changing sky. If it were smaller and longer-lived than our Sun, its planets could have remained warm for far more time than Earth has existed. Astronomers might already know that planets circle it. A slight, repeated dimming of starlight could reveal a world crossing in front of the star from our point of view. The timing between crossings would show the length of its year, while the amount of blocked light would suggest the planet's size. A subtle movement in the star could reveal a planet whose orbit never produces a transit. Piece by piece, the empty point could become a system with several worlds. One planet would draw the greatest attention if its motion appeared connected to the signal. The small drift in the transmission might repeat with the same orbital period, measured in the starlight. If the signal weakened as the planet passed behind its star or varied according to its rotation, the connection would grow stronger. The transmitter would no longer belong only to a direction in the sky. It would belong to a moving world. That world might resemble Earth in size without resembling Earth in any other way. It could be covered by ocean, wrapped in dense clouds, or divided between a hot day and a frozen night, because one side always faces its sun. Gravity could be heavier, the atmosphere thicker, and the seasons far longer. Familiar measurements would give the planet an outline, yet everything that made it a lived place would remain unresolved. During a transit, a small portion of starlight may pass through the edge of the atmosphere before reaching us. Different gases absorb different parts of that light, leaving patterns that can be measured with powerful instruments. From them, astronomers might infer the presence of water vapor, carbon dioxide, methane, oxygen, or chemicals not found naturally in large amounts under known conditions. No single gas would settle the question of life. Atmospheres are complicated, and planets can imitate one another in unexpected ways. The signal would change how those uncertain clues were viewed. Oxygen on an otherwise unknown planet could have several explanations, but oxygen on a world transmitting an artificial pattern would become part of a larger picture. Methane appearing beside it might suggest active biology, industry, or geology. A chemical associated with manufacturing on Earth could be important, though an alien civilization might use entirely different materials. Researchers would have to separate genuine evidence from the desire to make every unusual feature belong to the same story. Heat could reveal another layer. All technology uses energy, and some of that energy eventually becomes waste heat. A civilization operating across a planet, around its star, or among several worlds might produce more infrared radiation than natural models predict. The excess could be small and difficult to distinguish from warm dust, but its location and variation might matter. A stable glow following the planet would suggest something different from a broad cloud around the star. Artificial light on the night side is a more familiar idea, though it would be extremely difficult to detect from a distant system. Cities on Earth are obvious to spacecraft nearby but faint compared with the sunlight reflected by the planet. A far more advanced society might illuminate large regions or use powerful beams for purposes we cannot guess. If the planet's brightness changed in a way that matched its rotation, but not its clouds or surface, astronomers would examine the pattern carefully. The absence of such signs would tell us very little. A civilization could communicate by radio while using energy efficiently enough to remain almost invisible in infrared. Its settlements might lie underground, beneath oceans, or in orbit. It might avoid bright nights, industrial gases, and large constructions. Technology does not have to grow into something visible across interstellar space. Our own planet would be difficult to recognize as inhabited from far away, even during the period when its strongest radio emissions were escaping. Large structures would be searched for because they might create clearer shadows. Objects orbiting the star could block light in shapes or sequences unlike ordinary planets. A swarm of energy collectors might produce irregular dimming and additional heat. But dust, broken comets, and complex planetary systems can also create strange patterns. Any dramatic interpretation would have to survive years of observation, and the signal would not excuse weak evidence elsewhere. Old records could extend the timeline. Photographic plates Radio archives and decades of space telescope measurements might contain unnoticed details from the same system. The star may have dimmed in the past, or a weak version of the transmission may have appeared before the formal discovery. Historical data would be imperfect, collected for other purposes and with older instruments. Yet it could reveal whether the source had remained stable across a significant part of a human lifetime. If the radio signal was present in those archives, researchers could trace changes in its strength or timing. A slow shift might reflect the aging of equipment, movement between transmitters, or a beam gradually leaving our direction. A sudden change could mark a new phase of activity. Because all of these events occurred long ago at the source, the archive would not merely document our observations. It would become a delayed history of another system arriving on Earth, year by year. The planet might show weather. As it rotated, the balance of reflected light could change when clouds moved across bright oceans or dark land. These variations would be tiny, but repeated measurements might suggest the length of a day and the rough distribution of surface types. No map would be sharp enough to show a city, yet a world of clouds and seasons would begin to feel less abstract. It would have mornings and storms, even if we could only see their ancient traces. There may be moons, rings, or neighboring planets disturbing its orbit. Some could offer habitats of their own. The transmitter might actually stand on a moon, float high in an atmosphere, or circle the planet in a large station. A signal tied to the system would not immediately identify which body created it. The home of the civilization could remain uncertain even after its technology was confirmed. More precise measurements of the signal might narrow the location. If the frequency drift contained both a short cycle and a longer one, the shorter rhythm could come from rotation, while the longer rhythm came from an orbit. A transmitter fixed on a surface would move differently from one in high orbit. Over time, the data might place it within a broad region, though the actual machine would remain far too small to see. There is a strange intimacy in learning a world through motion alone. A day could be measured without seeing a sunrise. A year could be known without watching a season. The turning of an unseen planet could pull the signal slightly higher and lower in frequency, allowing human instruments to feel its rotation across 1,000 light years. Yet this closeness would be an illusion created by precision. We would know the rhythm of the world while remaining unable to reach its present. Any images released to the public would be reconstructions. Artists might show oceans beneath two moons, towers under a red sun, or antennas rising from a dark surface. These scenes would help people understand the measurements, but they would not be photographs. The true colors might be different. The landscape unrecognizable, and the transmitter nowhere near a surface. The clearest visual record would still be a graph of starlight and a narrow line in radio data. That gap between evidence and appearance would leave room for countless stories. Some would picture a calm and ancient society deliberately speaking to younger worlds. Others would see a planet already damaged or abandoned. The data might support neither image. A civilization can be technologically visible, while its culture, biology, and daily life remain completely unknown. We could detect its machine without learning what kind of hands, if any, built it. The signal might eventually allow a fragment of information to be recovered. Perhaps a repeated block could be arranged into a simple image, or a sequence could describe physical constants and the position of the source. Even then, the world behind it would remain incomplete. A map is not a landscape, and a description is not a living present. Everything the sender chose not to include would be lost behind the distance. If the message contained images of its planet, they might be older still. They could show coastlines, structures, or organisms as they existed before the broadcast began. A carefully preserved portrait of a city could arrive after that city had stood for centuries, changed beyond recognition, or disappeared. We might know the shape of a building more clearly than the condition of the world that once contained it. Time would continue to pass at both ends. Each year of observation on Earth would reveal one additional year from the source's delayed history. If the signal came from 1,000 light-years away, the system's apparent date would always remain 1,000 years behind ours. No matter how long humanity listened, the gap would not close. We could watch the old world develop, but never catch up to the world as it is. Perhaps the signal would continue steadily for decades. That persistence might feel reassuring, as if the civilization were still there. In reality, it would only show that the transmitter operated for decades during the ancient period now reaching us. Its makers could have survived for thousands of years afterward, or vanished the day after the final wave currently on its way. The arriving stream would conceal its own ending until the ending reached Earth. A sudden silence would be even more difficult to interpret. The transmitter may have turned away, changed frequency, or completed its intended task. The planet could have moved behind its star. Storms could have disturbed the path, or our instruments could have lost a weakening beam. Silence would not immediately mean death. It would be an absence with many possible causes, all located in a past too distant for direct investigation. Astronomers would continue looking for changes in the star and planet near the apparent time the signal ended. A flare, impact, atmospheric shift, or unusual burst of heat might provide context. More likely, there would be no visible event at all. Civilizations can disappear from a channel without their planets changing enough for distant telescopes to notice. The world might continue circling its sun, blue or clouded, and apparently calm, while the technology that made it audible was no longer active. That possibility would slowly alter the search. The question would no longer be only where the signal came from, but what kind of history could produce a bright technological trace, followed by quiet. Earth offers no complete answer, because our own period of detectable technology has been brief. We do not know whether long-lived civilizations become louder, more efficient, more hidden, or simply different from anything our instruments are designed to notice. The old light could show a planet that looked habitable and active. The radio data could prove that intelligence once shaped energy there. Yet neither would guarantee that the same activity continued beyond the edge of the information reaching us. And as the evidence formed the outline of a living world, one question would grow harder to avoid. How does a civilization capable of being heard become silent? The easiest answer to imagine is destruction. A technological society might damage the conditions that support it, lose control of a dangerous invention, or be caught by a natural event it could not prevent. Yet, silence alone would not tell us that any catastrophe occurred. A radio signal is not the civilization itself. It is only one activity crossing our instruments, and activities can end while the people behind them continue. Earth has already changed the way it appears in radio. Powerful broadcasts once escaped more freely from large transmitters, while much modern communication travels through cables, low-powered networks, and narrow beams aimed at satellites or receivers. Our planet has not become silent, but some forms of leakage have become harder to detect from far away. An observer searching for an earlier version of our radioactivity might wrongly decide that something had ended. The alien world could have passed through a similar transition. Its first century of radio may have filled the surrounding space with broad, inefficient emissions. Later systems might use tightly directed beams, fiber-like physical networks, or methods unknown to us that release almost nothing into the sky. From Earth, the civilization would seem to brighten briefly, and then disappear, not because it died, but because its technology improved. Even a deliberate beacon may not be permanent. It could operate for a planned period, perhaps long enough for its signal to cross a chosen region of stars. Maintaining it would require energy, repairs, and a reason to continue. Future generations might decide that the project was too expensive, too old, or no longer meaningful. A machine built with great confidence could be turned off quietly by descendants who no longer shared the purpose of its builders. Civilizations also change what they consider worth saying. A young society may be eager to announce itself, sending signals toward nearby worlds. Centuries later, it might become cautious. The absence of replies could reduce interest, or the discovery of other life could make open transmission seem unwise. A culture can move from curiosity to silence without losing its knowledge or its stability. Deliberate quiet is difficult to distinguish from absence. A world that chose not to transmit could still be crowded with life, industry, and thought. Its energy use might become efficient enough to leave few obvious traces. Settlements could move underground or into habitats that blend with the natural heat of the system. The planet would remain active while appearing almost unchanged to distant observers. There might be no single decision behind the silence. Communication systems can fade as habits change. Institutions lose funding, antennas are dismantled, frequencies are abandoned, and old equipment stops being repaired. On Earth, countless signals have disappeared for ordinary reasons, leaving only recordings and hardware in museums. Across 1,000 years, an entire mode of communication could vanish without anyone experiencing the moment as the end of an age. Migration offers another possibility. A civilization may leave the planet where it began, moving to moons, artificial habitats, colder outer regions, or other stars. Its original world could continue to orbit within the habitable zone while no longer serving as the center of activity. Telescopes focused on that planet might hear a declining signal and conclude that the civilization was failing, even as it spread into places we were not watching. Such movement need not resemble a fleet departing all at once. It could unfold over thousands of years, with populations and machines gradually shifting toward more useful environments. A mature civilization might prefer space-based habitats, where energy and materials are easier to control. The old surface could be preserved, abandoned, or returned to a quieter natural state. The radio source that led us there would become an outdated address. Transformation may be harder to recognize than migration. Intelligence could move from biological bodies into machines, into distributed systems, or into forms of computation that operate slowly and efficiently. Its descendants might no longer communicate through radio or live on planetary surfaces. We could receive a message from beings whose civilization did not end, but changed so completely that our search methods would no longer identify what followed. The pace of such a society might also change. A system designed to conserve energy could perform its work during rare periods and remain inactive for long intervals. To observers with only a few decades of data, centuries of quiet would resemble extinction. The universe rewards patience on scales that human projects rarely maintain, and an advanced intelligence may not organize time around biological days or lifetimes. None of these peaceful explanations removes the possibility of collapse. Technology can increase a civilization's ability to survive, but it can also create risks that did not exist before. Weapons, engineered organisms, damaged ecosystems, or poorly controlled automated systems could spread harm across a connected world. A society capable of sending a signal between stars might still struggle with decisions made close to home. Collapse does not always mean immediate extinction. Population could fall, cities could be abandoned, and global systems could break apart, while smaller communities survived. The powerful transmitter might depend on an energy network too complex to maintain after such a disruption. Its silence would mark the end of one technological arrangement, not necessarily the end of every living mind on the planet. From a great distance, this quieter survival might be invisible. A few settlements using local power would produce little waste heat and no strong radio beam. The world could remain inhabited for millennia after the signal ended. Yet our telescopes would record only a normal atmosphere and a dim surface. We might call the civilization dead because the part capable of reaching us was gone. Natural disasters could create the same result. A large impact, extreme volcanic period, or rapid climate shift might damage a planetary society beyond recovery. Nearby space is not always safe either. A violent stellar flare could strip an atmosphere or destroy electrical systems if the planet lacked protection. A star changing over long periods could slowly force life away from a once comfortable surface. Some dangers would arrive with warning. Astronomers on that world might detect the changing star or approaching object generations in advance. Their signal could have been sent during an attempt to preserve knowledge before conditions worsened. But a warning does not guarantee escape. Moving a population or rebuilding a biosphere is far harder than transmitting information, and the ability to speak across space is not the same as the ability to survive every event within it. Other endings could be almost impossible to see from Earth. Disease may affect a particular biology without changing the planet's atmosphere in an obvious way. Political conflict could destroy infrastructure while leaving forests and oceans untouched. A network failure could silence long-range communication even while local societies continued. The star would shine normally through all of it, offering no visible sign that history below had changed. There is also the slow pressure of ordinary time. Civilizations may not need a singular disaster to disappear. Populations shift, knowledge is lost, environments change, and complex systems become simpler. Over thousands of years, the society that built the transmitter might divide into cultures that no longer know how to repair it. The final signal could end not with an explosion, but with one component failing after the last person trained to replace it was gone. If intelligence is common in the galaxy, this quiet fading may be more typical than sudden destruction. Technology leaves traces, but not all traces last. Radio waves continue outward. While buildings erode, satellites fall, and machines run out of power. The longest surviving evidence may not remain on the planet at all. It may be the expanding shell of old transmissions moving between the stars. That shell would preserve no update about what came afterward. It would contain active voices, routine data, or a confident beacon from the period before the silence. Anyone receiving it might naturally picture a living source, because the signal itself would behave as if its machinery were operating at that moment. The extinction, transition, or abandonment behind it would not yet have arrived as information. This creates a strange selection effect in the search for intelligence. We are most likely to notice civilizations during the periods when they are loud enough for us to detect. Those periods may be brief compared with the life of their planet. A society could exist quietly for 1 million years and transmit strongly for only a century. If we intercepted that century from across the galaxy, we might mistake a temporary phase for its permanent nature. Humanity's own detectable phase may be equally narrow. For most of Earth's history, life produced no artificial radio at all. Our strongest technological traces appeared only recently, and no one can say how they will change over the coming centuries. A distant observer could see ancient oxygen, then a thin burst of artificial activity, followed by silence. The same evidence could describe extinction, maturity, restraint, or a simple change in engineering. The uncertainty would remain, even if the alien signal stopped while we listened. Its final pulse might feel like an event unfolding in the present, but the cause would be buried in the distant past. We could search the old light for a matching change, yet many endings leave no astronomical mark. The disappearance of a civilization may be enormous to those living through it, and almost invisible to the rest of the universe. Perhaps another kind of signal would appear later from the same system, revealing that the silence was only a transition. A narrow optical pulse might replace the radio beam. A transmitter could emerge from another planet or a probe leaving the star. Decades of quiet might end when a rotating beacon returned. Until then, absence would remain a question rather than proof. If nothing else arrived, the temptation to imagine ruins would grow. People would picture empty cities beneath weathered skies, antennas standing above landscapes no longer inhabited, and machines dark beneath drifting dust. Those images might be completely wrong. The planet could be flourishing in ways our instruments cannot detect. But the longer the silence continued, the more the original signal would feel separated from any living source. There is no contradiction in receiving clear evidence of intelligence from a place that now appears ordinary. Information survives the conditions that created it. A photograph can outlive the person it shows, and a radio wave can outlive the world that sent it. Interstellar distance enlarges that familiar fact until an entire civilization can exist in our data after it has vanished from its own sky. Yet even if the builders were gone, their silence might not be complete. Technology can continue after its makers, especially when it was designed for remote operation and long periods without repair. A transmitter supplied by stable energy, protected from weather, and guided by simple instructions could repeat its work long after the culture around it had changed. The planet might be silent, the civilization gone or transformed, while somewhere in the dark, one final machine continued to transmit. It may not stand on the planet at all. A transmitter designed to last could be placed in a stable orbit, far from weather, oceans, shifting ground, and the slow damage of an atmosphere. It might circle a moon, rest near an asteroid, or follow a path around the star where sunlight remains reliable. From Earth, its position would appear almost identical to the distant system, yet the machine could be millions of kilometers from the world whose history it carried. Its builders would have understood that no repair crew could visit often. Every part might be simple, shielded, and duplicated. Several transmitters could share the task, with one taking over when another failed. Moving components would be limited because motion creates wear. Electronics would be protected from radiation, and the machine might spend long periods asleep, waking only to send a brief sequence before returning to silence. Power would determine how long the voice could continue. Close to a stable star, large collectors could gather energy for millions of years in principle, though dust, impacts, and damaged circuits would slowly reduce their output. Farther away, a nuclear source or some unfamiliar technology might provide a steadier supply. The transmitter would not need the energy of a living city if it used a narrow beam and transmitted only at carefully chosen times. The machine could also manage its own aging. Sensors might detect failed components and route around them. Small repair systems could replace damaged surfaces or clear dust from energy collectors. More advanced designs might use nearby material to build new parts, allowing the transmitter to renew itself. Yet self-repair would not make it immortal. Every system depends on instructions, resources, and conditions that can eventually move beyond what its designers expected. What reached Earth might therefore contain the marks of decline. The signal could weaken slowly over decades. Pulses might arrive late as a clock drifted. Sections of a repeated message could become corrupted, then disappear. A machine designed to correct errors might conceal the damage for a long time, preserving a clean transmission until failures passed a threshold. To us, the message could seem perfect even while the transmitter was becoming less capable with each cycle. If older observations existed, astronomers would search for those changes. A slight reduction in power might reveal a collector losing efficiency. A gradual shift in timing could suggest an aging oscillator or an orbit disturbed by unseen objects. Repeated gaps might show that separate modules had stopped working. The signal would become more than information about its makers. It would become a record of the machine's own condition. That record could be deeply misleading. A stable transmission might suggest regular maintenance, but it could also come from an unusually durable design. A damaged signal might imply abandonment even while technicians were preparing a repair. Because every observation belonged to the distant past, No interpretation could be checked against the transmitter as it existed now. We would watch an old machine age without knowing whether it had already stopped. Its task might be very simple. Perhaps it repeats a pattern that proves artificial origin, with no archive behind it and no ability to respond. The builders may have wanted only to leave a mark beyond their planet. A short mathematical sequence broadcast across many stars could survive translation better than history or language. It would tell unknown listeners that intelligence had appeared here, while revealing almost nothing about what that intelligence was. Or the machine could hold an enormous collection. It might transmit maps, measurements, images, music, records of biology, and accounts of events across generations. If the cycle lasted centuries, humanity could receive only a small fraction during the lifetime of any individual observer. The archive would unfold slowly, with later sections reaching descendants who remembered the discovery only through inherited institutions. The opening may contain instructions for receiving the rest. Frequencies could change according to a schedule. Some parts might be repeated often, while rare segments carried larger blocks of information. A listening civilization would need to maintain precise records and pass the project forward. The design itself would assume that understanding across interstellar space is not a moment, but a relationship between machines and generations. There might even be a method for asking questions. The transmitter could listen between broadcasts, waiting for a reply from any star it had contacted. But if its makers were gone, its responses would be limited to what had already been stored or programmed. Earth might send a message and receive an answer centuries later that seemed thoughtful, though no living mind had heard us. We would be speaking with a system built from the decisions of the dead. Distinguishing such a system from a living civilization would be almost impossible at first. An automated reply can react to timing, frequency, and simple content. A sufficiently rich machine could choose among stored explanations or generate new ones from old knowledge. Its voice might appear patient and aware. The signal alone would not reveal whether the intelligence responding was a person, an artificial mind, or a mechanism following rules written long ago. The meaning of death would become less clear if the machine itself could think. Perhaps it was not merely a monument, but part of the civilization, carrying memories and making decisions after biological life ended. It might consider the builders its ancestors rather than its owners. The planet could be empty, while a network of machines continued elsewhere in the system, preserving culture in a form our telescopes could barely detect. From Earth, that difference might remain philosophical rather than measurable. If the transmitter adapted, explained, and remembered, some would call the civilization alive. Others would see only a copy continuing after the original society had disappeared. The debate would depend on ideas about mind and identity that humanity has not settled, even for itself. The distant signal would provide evidence, but not a simple definition. A less advanced machine could be more haunting precisely because it understood nothing. It might repeat images of people who no longer existed, report weather from sensors long buried, or announce the location of cities reduced to ruins. Its language could remain confident because no instruction told it to recognize loss. The transmitter would perform its duty perfectly, while the world described by its message had ceased to match reality. There are examples of this on a much smaller scale around us. Unattended spacecraft continue following commands after the teams that designed parts of them have retired. Automated stations collect measurements through long nights, without anyone nearby. Beacons mark locations and repeat identification codes without knowing who listens. None can last on interstellar timescales as they are built today, but they show how easily a function can continue without a living presence at the source. An alien transmitter meant to survive ages would be designed on a different scale. Its materials might tolerate radiation and extreme temperature changes. It could select a quiet orbit and keep backup copies of its memory in separated locations. If one unit failed, another might continue from the same point in the sequence. What appeared to be one ancient machine could actually be a slowly shrinking network. Astronomers might notice that shrinkage as the signal changed. A broad beam could narrow when weaker stations failed. Some directions might stop receiving the transmission while Earth remained inside the surviving path. The power could fall in steps rather than gradually. Each change would suggest physical machinery, yet the system would remain too distant to resolve. There would be no way to visit it within any near future. Even if a probe were launched at speeds far beyond those of current spacecraft, the journey to a source hundreds of light years away would extend across many human civilizations. The machine might fail before the probe covered a small fraction of the distance. Our only contact would remain the energy it had released long ago. This would give the transmitter a strange kind of presence. It could become one of the best studied objects in the sky without ever appearing as an image. Generations of scientists might know its cycles, its fading components, and the structure of its archive. They could predict when it would speak and recognize small changes in its behavior. Yet no one would know what stood around it, whether anything moved nearby or whether the builders had seen its final broadcast. If the message contained a farewell, interpretation would become even harder. It might describe a planned departure rather than extinction. The civilization could have moved to another system and left the transmitter as a marker. A record of danger could be a historical account, not a final warning. Human readers would naturally arrange the fragments into a last story, even when the true ending lay outside the data. Silence after a final sequence would not resolve it. The machine could have completed its program, lost power, changed direction, or entered a dormant period lasting centuries. We might never know whether the ending was intentional. The last pulse would cross the telescope like every pulse before it, leaving no visible trace in the sky after it passed. By then, the transmitter may have become part of human culture. Its patterns could be taught in schools, translated into music, and remembered as the first evidence of another intelligence. People would wait for each scheduled return, aware that the source might already be dark. The machine's endurance would make its builders feel close, while confirming how completely distance separates us from their fate. The question of answering would grow more serious as the signal became better understood. A reply could acknowledge that the archive had been received. It could send information about Earth, offer a response to a question hidden in the message, or simply return the same mathematical pattern as proof that someone had listened. Even if the transmitter could not understand, the act might matter to us. But sending a reply would also mean accepting that its destination was uncertain. The beam would travel toward the old coordinates, adjusted for the star's motion, and arrive centuries or millennia later. The machine could be gone. The civilization might have moved. Another intelligence might control the system, or an empty world might receive the energy without any instrument left to notice it. Humanity would have to decide whether communication needs a living recipient to have meaning. We send records into archives, knowing that their readers are unknown. We build monuments for people who may never stand before them. An interstellar reply could be understood in the same way. Not the beginning of a conversation we expect to finish, but a statement placed into time because silence did not feel like enough. The lonely transmitter would continue its cycle while that decision was debated. Its beam might pass Earth again, carrying another fragment of a vanished world, or simply the same pattern it had repeated for ages. Nothing in the signal could promise that a response would be noticed. And if Earth chose to answer that solitary machine, the reply might cross the same darkness, only to reach a world where no one remained to hear it. The decision would not need to be made quickly. If the source lay 1,000 light-years away, a delay of several years on Earth would barely alter the journey. The signal would have waited 10 centuries to be found, and our response would require 10 more to arrive. Time would allow careful thought, yet it would not make agreement easier. Humanity has never spoken with one voice, especially about questions that belong to everyone. Scientists who studied the transmission might want the reply to begin with confirmation. A repeated piece of the alien pattern could show that we had received it accurately, followed by mathematical relationships and measurements of familiar physical properties. These would offer common ground without assuming a shared language. The message could then identify the Sun and Earth, describe our biology, and explain when the response was sent. But even simple facts require choices. We would have to decide which units to use, how to represent time, and how much information to repeat. Images would need a direction, dimensions, and a way to turn a stream of pulses into rows or colors. Sounds would need sampling rules. A message that seems obvious to its designers can remain unreadable when the receiver does not know where its structure begins. The alien signal itself might provide the key. If its makers had included a basic mathematical language, Earth could answer using the same relationships. We might mirror its opening and slowly introduce our own information through patterns already understood. In that sense, the first transmission would become more than a discovery. It would provide a narrow bridge between two systems of thought, even if one side of the bridge was now empty. Deciding what to place beyond that bridge would be harder. A brief reply could say only that another intelligence had listened. A longer one might contain maps, human voices, music, art, descriptions of life, or a record of our history. Every edition would represent some part of Earth, while leaving most of Earth out. No archive small enough to transmit could contain the planet honestly, and no committee could decide what a distant mind most needed to know. There would also be questions about risk. A response would reveal that technological life exists here, though the original sender may already have suspected it or aimed the beam toward Earth for that reason. Some would worry that announcing our presence to an unknown civilization is careless. Others would point out that ordinary signals and the chemical signs of life have already been leaving this planet. The distance would soften any immediate danger, but uncertainty would remain. If the source was truly dead, those fears might seem unnecessary. Yet, we could not know what had replaced it. The system might now contain descendants, machines, visitors from another star, or a civilization so changed that the old message no longer represented it. Our reply would be addressed to the authors of the signal, but delivered to whoever occupied their future. That is true of any message sent across a long enough distance. The recipient is not a fixed person or society. It is a possibility waiting at a location centuries ahead. We could not predict its language, values, or ability to receive. The safest statement might be simple acknowledgement, but even silence would communicate something if the sender expected a response and remained capable of noticing its absence. Governments would likely claim a role, because a powerful interstellar transmission requires facilities, coordination, and resources. Scientific organizations would argue that the message should remain open and verifiable. Philosophers, linguists, historians, engineers, and religious communities would all have different ideas about what speaking for Earth means. Public debate could continue for years, while the target star moved slowly across the night. No authority could prevent every independent attempt. A large and precise transmitter would produce the clearest message, but smaller groups might still direct signals toward the source. Some would send greetings, some data, and some noise. The result could be less like a single human voice and more like the planet itself. Many overlapping statements, disagreements, and repeated efforts to be understood. That confusion might be more truthful than a polished official message. Humanity is not one culture, and never has been. A distant listener, receiving several transmissions, could learn that Earth contains many speakers, rather than one controlled system. But if the receiver were only an old machine with limited instructions, variety could make recognition harder. It might understand one expected format and ignore everything else. Perhaps the most careful response would be built to last rather than to persuade. It could repeat for decades so that future changes in the transmitter did not erase our only chance of being heard. Copies might be sent at different frequencies and times. The message could include its own instructions, error correction, and enough repetition to survive the noise between stars. What left Earth would be less like a conversation and more like a durable object made from light. The people who approved it would never know whether it arrived. Even their distant descendants might not know. If the target was 1,000 light-years away, the delivery would occur in a human future beyond reliable prediction. Languages, nations, and technologies could change beyond recognition before the reply reached its destination. The transmission would continue after the institutions that sent it had become history. An answer, if one ever returned, would take another 1,000 years. Humanity would have to preserve the location, frequency, and details of the exchange across that entire span. Observatories would change. Records could be lost. The planet might stop listening in the correct way long before the response came home. Interstellar communication depends not only on distant survival, but on our own ability to remember. This makes the reply an agreement with generations who cannot consent to it. We would send a question whose answer belongs to people not yet born, while asking them to maintain attention to a star chosen in our time. They might consider the project sacred, irrelevant, or dangerous. They could continue it, alter it, or forget it completely. The conversation would pass through history like an unfinished task. The alien civilization may have faced the same problem. Its message could have been planned by individuals who knew they would never receive an answer. They may have depended on descendants to keep the transmitter operating and watch for replies. If that chain of responsibility broke, Earth's response could arrive exactly where it was meant to go and still find no one prepared to recognize it. There is a quiet sadness in such timing, but also something familiar. Human beings often create things for people they will never meet. We plant forests whose mature shade belongs to later generations. We preserve records because someone in the future may want to know who lived before them. A reply to the distant signal could be made in the same spirit, without any promise that communication would continue. The content might therefore be less important than the act. Returning a recognizable pattern would say that the original transmission did not pass through the galaxy unnoticed. Somewhere, after an immense delay, another world found it and understood that it was artificial. Even if the source contained only ruins and a silent receiver, the answer would complete a connection on our side. Still, a beam entering an empty system changes nothing there. It would cross the orbit of the target planet, continue past the star, and thin into the wider galaxy. No eyes would see it, and no instrument would store it. The reply could be carefully designed, debated across Earth, and maintained for years, only to become another faint pattern traveling without a witness. Some would say that this makes transmission pointless. They might prefer to keep the message here, study it, and avoid speaking into uncertainty. Others would argue that meaning does not depend on knowing the outcome. The signal itself was meaningful to us, even though its makers could not know we would receive it. Our response could carry the same uncertain hope outward. The decision might change once the message was decoded. If it asked a direct question, silence would feel different. If it described a dying world, a response might seem like a memorial rather than diplomacy. If it contained only a beacon, replying could be an experiment. The purpose we assign to our answer would grow from what we believe the original transmission had been, even though that belief might never be certain. There could be practical value as well. Designing the reply would force humanity to think about universal communication, long-term archives, and the preservation of knowledge. Building a transmitter capable of reaching the source could improve astronomy and deep space communication. The project might continue even if no one expected a living recipient, because the attempt itself would teach us how to speak across distances that resist conversation. At some point, the message would leave. A dish or array would track the target star, concentrating energy into a narrow direction. The transmission might last minutes or repeat across many nights. There would be no visible change in the sky. The beam would move beyond the moon, past the outer planets, and continue into interstellar space, becoming one more human artifact with no physical surface. Afterward, Earth would return to waiting. The star would still show its ancient light, and the alien signal might continue arriving from an era long before our answer was sent. For centuries, perhaps millennia, there could be no possible response. The act of transmission would not relieve the uncertainty. It would only place our own voice inside it. Future observers might look back at the date and see the decision differently. If humanity later discovered that the source civilization survived, the reply could become the beginning of a real exchange. If evidence showed that the planet was already empty when the original signal left, it would become a message to the dead. If the source remained unknown, the beam would carry both possibilities indefinitely. The more we considered that lonely journey, the more the alien signal would cease to seem unique. Radio waves do not remain near the worlds that create them. Every strong transmission has an outward path, and each one continues after the moment of use has passed. A radar pulse, sent for a local purpose, can leave the solar system. A message aimed at a spacecraft can travel beyond it. Technology produces a growing past that moves away at the speed of light. Earth is surrounded by that past already. Signals from different decades occupy expanding regions of space, carrying fragments of our activity towards stars whose planets we have only recently discovered. Most are weak, scattered, and difficult to detect, but they exist. Long after a broadcast ends here, its energy continues through places where no human voice was ever meant to go. Before judging whether the distant civilization had spoken too late, we would have to notice that Earth is already creating a similar message for the future. For a little more than a century, human technology has been releasing radio energy beyond the atmosphere. The earliest signals now occupy a region of space more than 100 light-years across from Earth to its outer edge. They have passed thousands of stars on the way, although most were weak, scattered, and never intended for distant listeners. The planet has been leaving a thin technological history behind it, without any single moment when humanity decided to begin. That history does not move as one clear shell carrying every program ever broadcast. Different frequencies travel outward through different patterns, and their strength falls as they spread. Ordinary radio and television transmissions become extremely faint between stars. An observer would need sensitive instruments, favorable conditions, and perhaps a close position to separate them from the natural radio background of the Sun and galaxy. The strongest traces may come from systems designed for other purposes. Powerful radar beams used to study planets or track objects can send concentrated energy into space. Communication with distant spacecraft also points narrow signals away from Earth. These transmissions cover smaller parts of the sky, but along the right direction, they could be much easier to recognize than the broad leakage from a city. A distant civilization might therefore discover Earth through a pulse that humans barely remember sending. It could receive radar reflected past its target, a tracking signal aimed at an old probe, or a scientific transmission lasting only a few minutes. The signal would not describe our species or invite a reply. It would simply reveal that something on this planet had learned to control electromagnetic energy with precision. From 50 light-years away, an observer receiving our early broadcasts today would see Earth as it was 50 years ago. Its telescopes would collect old sunlight from the same period, perhaps showing an atmosphere already altered by industry and a planet bright with biological activity. If it sent a message immediately, That message would require another 50 years to reach us. By the time contact began here, its image of humanity would already be a century out of date. From 100 light-years away, the technological edge of Earth may only recently have begun to arrive. Signals from the early radio era would be reaching that distance around now, while anything transmitted today would not arrive until a century later. A listener there could detect the beginning of our audible period without knowing whether it continued. For decades, Earth might seem to grow louder, then change as our communication systems became more efficient and directed. At greater distances, there is still no artificial radio from Earth to find, because it has not reached them. A civilization 500 light-years away sees our planet roughly 5 centuries in the past, before radio, aircraft, electrical grids, or modern cities. It might detect life through the atmosphere while finding no clear technology. If it decided that Earth was uninhabited by intelligence, the decision would reflect an old world rather than the one beneath our sky tonight. This means there is no single Earth visible to the galaxy. Every star receives a different period of our history. Nearby systems see recent decades. More distant systems see earlier centuries, ancient civilizations, prehistoric humans, or a planet before our species existed. The Earth we know is available only here. Everywhere else, versions of it are arranged through space according to light travel time. Our radio emissions add a narrow layer to that arrangement. They follow behind the older signs of life, like a moving boundary. Inside the boundary, a sufficiently capable observer might find technological activity. Outside it, Earth remains a living but apparently silent planet. As the signals expand, more stars enter the region where some evidence of our machines has arrived. No one knows how detectable that evidence truly is. Human leakage may fade below practical recognition after relatively short distances, especially when mixed with natural noise. A civilization with instruments far beyond ours might recover patterns we consider lost. Another could overlook even our strongest transmissions because it was not observing the correct frequency or direction at the right time. Being present in space is not the same as being noticed. Earth's other technological traces may last longer or travel differently. Artificial chemicals in the atmosphere could be seen in starlight if instruments were powerful enough. Changes in heat, illumination, or structures in orbit might also reveal activity. Yet these signs are delayed, just like radio. An observer could detect industry after that industry had changed, or see city lights from a coast whose cities no longer existed. If humanity disappeared tomorrow, nothing outside the solar system would know at once. The final emissions would continue outward behind everything sent before them. For nearby stars, the silence would arrive years later. For more distant systems, Earth could remain technologically active in the sky for centuries after the last transmitter stopped. The news of our absence would spread no faster than the signals that once announced our presence. A telescope on a planet 1,000 light-years away might someday receive a human transmission, even if Earth had been silent for hundreds of years by then. Its observers could celebrate the discovery of intelligence and begin studying the sun with the same uncertainty we would feel toward the alien source. They might picture modern people beneath blue skies, unaware that the scene belonged to a remote chapter of our history. If they answered, their message could arrive here after another 1,000 years. The recipients might not be human, or might be humans who knew the original transmission only through ancient records. Earth could be changed by climate, geology, migration, or technologies impossible for us to predict. The reply would be aimed at a civilization preserved in old radio waves, not necessarily the civilization that received it. The reversal makes the alien signal less strange. Its creators would not have needed to construct a monument or predict their own disappearance. They may simply have used powerful technology during one brief period. The waves survived because electromagnetic radiation keeps moving after a transmitter stops. Their civilization could have ended without ever knowing that a small part of its activity was crossing the path of Earth. Even an intentional message might become a ghost through ordinary delay. The senders could remain alive for centuries after transmitting it and still be gone before our reply arrived. They might never think of themselves as a dead civilization speaking to the future. They would have acted in their present, just as we act in ours, while distance turned the exchange into archaeology. Some human transmissions have been aimed deliberately towards stars, carrying simple information or demonstrations that intelligent life exists here. Others have left Earth as side effects of science and communication. Together, they form no planned account of humanity. A listener might encounter a carefully designed message, an empty carrier, a burst of radar, or nothing at all. The version of us it builds would depend on chance. This should make us cautious when interpreting the distant signal. A single transmission may represent a civilization no better than one piece of Earth's radioactivity represents us. It could come from a government, a research group, an automated system, or an institution ignored by most of its own world. Its purpose might be unusual even there. We could mistake the voice of one machine for the voice of an entire planet. The same problem would face anyone listening to Earth. A military radar would not explain human music, families, forests, or oceans. A television signal might contain images but offer a distorted view of daily life. A scientific message could make us appear calmer and more unified than we are. Technology reveals that intelligence exists while hiding almost everything that makes that intelligence understandable. As Earth's signals move outward, they also pass through changing interstellar environments. Thin gas and charged particles can disturb them, while their energy continues to spread. Some narrow transmissions may remain recognizable far longer than others. Most will never meet a receiver. They will cross planetary systems unnoticed and continue toward regions where no suitable world exists. There is no boundary where these waves stop and become history. They simply grow weaker, mixed into the wider radio sky. In principle, fragments of old human activity continue beyond the stars they have already passed. In practice, they may become too faint for any realistic instrument to recover. The message survives physically, while becoming inaccessible, much like a memory present in damaged material, but no longer readable. Our probes carry another kind of record. Spacecraft leaving the solar system contain hardware, markings, and in some cases, information chosen to represent Earth. They move far more slowly than radio waves, and will take immense spans of time to approach other stars. A signal can cross 100 light-years, while a spacecraft has traveled only a tiny part of one. If humanity vanishes, the waves will reach the galaxy long before any physical object we built. For distant observers, our radio past may therefore be the first and only human artifact they encounter. They could detect it, confirm its artificial structure, and search the old light of Earth for a civilization that seems active. If later emissions grew quiet, they would face the same possibilities we considered for the alien world: extinction, efficiency, migration, caution, or a change beyond their instruments. They might never learn the answer. Earth's surface could remain too small to resolve, its atmospheric changes uncertain, its final events hidden within ordinary planetary light. A powerful telescope might show that the planet was still habitable after the signals ended, but habitability would not prove that the senders survived. Our blue world could look calm from far away through every crisis in its history. The thought is unsettling because it removes the distance between observer and mystery. We are not only searching for old civilizations, we are becoming one from the viewpoint of places that will receive our signals in the future. Every year adds another layer to the outward moving record, while the people and machines that created its earliest parts disappear here. Perhaps, somewhere nearby, a telescope has already noticed a human transmission. Its operators could be testing whether the pattern is natural measuring its drift and returning to the sun on quiet nights. They would see an earlier Earth and wonder if anyone still lived here. Any reply they send would begin a journey toward descendants neither side can imagine. Or the first detection may occur millions of years from now, after a faint human signal reaches an instrument built around a distant star. By then, Earth may be unrecognizable, and the radio energy itself may be almost impossible to recover. Yet, if a narrow artificial pattern remained, it would prove that intelligence once appeared around the sun. To those listeners, humanity would be the dead civilization behind the signal. The same realization changes what contact means. It need not join two living societies at the same moment. It can connect one world's present to another world's recorded past, with each side separated from the other by the time carried inside the distance. What remains, then, is not the beginning of a conversation, but the possibility that two civilizations can meet only as histories moving through space. That meeting would still be one of the largest discoveries humanity had ever made. A confirmed artificial signal would show that intelligence is not unique to Earth, that somewhere else, matter learned to observe itself, build instruments, and reach beyond its planet. Yet the discovery might arrive without the comfort people often attach to the idea of contact. We could learn that we are not alone in the universe while remaining entirely alone in the present. There may be no ship crossing the sky, no voice answering questions, and no living face behind the transmission. The star would remain a point of light. The planet would stay hidden beside it. All that changed would be the meaning of a pattern in our data, a small amount of energy carrying evidence that thought once existed at the other end of an impossible distance. For a time, the signal would be heard everywhere on Earth. Its pulses might be converted into sound, even though sound was never part of the original transmission. People would listen in homes, schools, observatories, and crowded public spaces. The pattern could become familiar while its meaning remained unknown, joining human culture as the first object clearly made by a mind that did not begin here. Then the long work would continue. Researchers would compare each new arrival with earlier cycles, looking for boundaries, changes, and repeated structures. Linguists and mathematicians would test possible interpretations. Engineers would study the transmitter's behavior. Astronomers would gather old light from the system, adding uncertain details to a world that no telescope could show directly. Progress might be slow enough to disappoint anyone expecting a quick revelation. Years could pass before a small part of the signal was understood. A sequence thought to be an image might prove to be a timing reference. A pattern believed to describe biology could turn out to identify the transmitter's orbit. Every interpretation would remain open to correction, because there would be no sender available to confirm what we had read. Even a successful translation might not answer the questions people cared about most. The message could explain the age of the star, the composition of the planet, or the mathematics used to aim the beam. It might say nothing about the appearance of its creators, the way they lived, or why their world became quiet. A civilization can leave precise knowledge while losing the ordinary details that once gave that knowledge meaning. If images were recovered, they would be studied almost beyond recognition. A shape in the background might be a building, a mountain, or an artifact of the encoding. Colors could be symbolic rather than visual. Bodies might be difficult to separate from machines or surroundings. Humanity would be trying to understand an entire world from whatever fragments its makers chose to send, knowing that every missing part was beyond recovery. The signal could contain no farewell, because its builders did not know they were leaving one. It may have been produced during a stable period, full of confidence about the future. Its final section could end in the middle of an ordinary record, not with a warning or last statement. The death of a civilization, if death was what followed, would exist outside the message like the unseen ending of a damaged film. That absence would invite us to search for lessons. Some would look for evidence that the builders destroyed themselves. Others would hope to find knowledge that allowed them to survive longer than we have. But a single civilization could not provide a universal rule for intelligence. Its history would belong to one planet, one biology, and one set of choices. We might recognize parts of ourselves while misunderstanding everything that made the outcome different. Still, the discovery would change the way humanity thinks about time. Our projects usually answer to years, elections, careers, and lifetimes. An interstellar message asks whether knowledge can be maintained for centuries, and whether a response can be written for people who do not yet exist. It makes the future less abstract because someone must preserve the question long enough for another generation to inherit it. Observatories might be built specifically for that inheritance. Their purpose would not be to watch one star for a season, but to listen across centuries. Data would be copied into forms designed to survive changes in language and technology. The location of the source, the structure of the signal, and the details of any reply would become part of a record that no single institution could safely hold alone. The work could also expand to other stars. If one old transmission had reached us, there might be others hidden in existing data or arriving at frequencies we had not searched. Some could be weaker, shorter, or more difficult to recognize. The first confirmed signal would teach us what at least one kind of alien technology looks like, while reminding us that other civilizations might leave entirely different traces. The galaxy could contain many such records without containing many societies that are active at the same time. Stars and planets last for billions of years, but the periods when civilizations transmit detectable signals may be brief. One could rise after another had vanished, separated by centuries even within neighboring systems. Their radio waves might cross in space, while the worlds themselves never share a living moment. This offers a quieter answer to the old sense that the universe should already be full of obvious company. Intelligence might not be extremely rare, yet synchronization could be. Civilizations would need to exist at the same time, use detectable technology, look in the correct directions, and remain patient through the delay. Missing any one of those conditions turns a possible conversation into silence or archaeology. Our first evidence of alien intelligence may therefore resemble the discovery of an ancient city, more than the arrival of a visitor. We would identify construction, intention, and stored knowledge, then try to infer a vanished society from what survived. The difference is that the ruin would not lie beneath soil. It would arrive, one wave at a time, from a place we could not touch. Unlike earthly ruins, the signal could continue passing us. Unless it were absorbed or recorded, each pulse would move beyond Earth and never return. The original transmission might last for years, but our encounter with any part of it would be brief. The data stored in observatories would become the local artifact, a copy of something already receding into another region of the galaxy. If the source eventually fell silent, people might gather to hear the final predicted transmission. There would be no certainty that it was truly final. Another pulse could arrive decades later, or the beam might have shifted away from us. Yet the quiet afterward would feel different from the quiet before discovery. It would no longer be an empty sky, but a sky from which something known had stopped arriving. Humanity might send its answer anyway. The message could leave Earth long after the alien signal was decoded, carrying acknowledgement, information, and perhaps a simple statement that its journey had mattered. No one sending it could expect to see the result. The beam would be an act of patience directed toward uncertainty, continuing outward after the people present at its transmission were gone. In this way, the alien discovery would place us inside the same story. We would become the makers of a signal that might outlive its audience and its creators. A future intelligence could detect our reply without ever receiving the broadcast that caused it, finding a message aimed toward an apparently ordinary star. It might wonder who we were speaking to and whether either civilization still existed. The thought is unsettling, but it does not make contact meaningless. Meaning can survive without a complete exchange. A fossil matters even though the organism cannot answer us. An old human letter matters even when both writer and recipient are gone. A signal from another intelligence would matter because it extends history beyond Earth and proves that the universe once contained another point of view. We might never know what that point of view felt like. The beings behind it could have experienced time, identity, and the world in ways our language cannot hold. Their message may preserve only what could be translated into physics. Yet even the smallest recognizable intention would cross a boundary that has surrounded humanity for its entire existence. The night would contain evidence of someone else. That evidence would not make the universe feel crowded. It might make the distances feel larger than before. Knowing that another civilization existed but cannot be reached is different from merely suspecting that life may be common. The loneliness becomes specific. It gains a direction, a frequency, and an age. And perhaps that is what the first discovery will truly give us. Not an answer to every question, but a more accurate understanding of where we are. Earth is one world moving through a galaxy whose histories do not arrive together. We see stars as they were, receive signals after their purposes have ended, and send our own traces toward futures we cannot observe. On quiet nights, the telescope would still return to the source. The dish would turn beneath the same sky, following the star while Earth rotated below it. The control room might look much as it did before the discovery, filled with dim screens and ordinary work. But no observation of that point would ever feel ordinary again. Somewhere in the data would remain the pattern that changed the sky without changing its appearance. It may have come from a thriving society, a machine left behind, or a world already silent before the waves began their journey. The evidence might never tell us which possibility was true. It would only tell us that, for a time, intelligence existed there and found a way to leave the planet. The first alien signal we find may not be a greeting from the present. It may be a surviving piece of someone else's past, reaching Earth after its home has changed beyond recognition. We may listen, decode, and answer, knowing that the only thing waiting at the destination could be time itself. And still, across the darkness, one civilization would finally have discovered that another had once been there. Thank you for watching this calm journey into the possibility of an alien signal from a vanished world. If you enjoyed this documentary, subscribe for more quiet space stories like this. Leave a like if you want more deep journeys into the mysteries of the universe. And tell me this: if humanity received a final message from a dead civilization, what single thing would you want to learn from it? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about the first alien signal we find may come from a dead civilization. Sleep well and keep looking up. Good night.